All right, so today we're doing something a little different. We're not just going to talk about statistics. No, we're going to become data detectives. We're on a mission to crack the case, to find the real story that's hiding in all the numbers we see every single day. You ready? Let's dive in.
So, to kick off our investigation, I've got a little riddle for you. How on earth could an ordinary shopkeeper, back in the 1600s, we're talking no computers, no fancy calculators, how could he possibly know more about his own city than the people actually running it? The answer to that question? Well, that's where our whole story really begins.
And that question leads us right to our very first case file, the original data detective. We're going to be looking at this guy, John Grant, and the surprising clues he used to crack the case, something called the Bills of Mortality.
I want you to picture London in the 1660s. It's a mess. It's chaotic. There's no official census, no reliable records of anything. The government literally had no idea how many people lived there. The only scraps of data they had were these weekly reports, these bills of mortality, which basically just listed who died and what they died from. To most people, they were just, grim lists. But to John Grant, they were a treasure map.
Okay, so Grant's method? It was so simple, it was brilliant. Look, he couldn't knock on every door in London, right? So he started small. He went to a few neighborhoods, parishes, they called them, and found that on average, about 3 out of every 88 people died in a year. Then he grabbed a second clue, the official citywide record, the Bills of Mortality, which said 13,200 people died that year in total. And just like that, with those 2 little pieces of information, he had everything he needed to solve this massive puzzle.
And the result was absolutely groundbreaking. He just scaled up his little sample, did some simple math, and calculated London's population to be about 387,200 people. I mean, think about that. For the very first time, somebody had used a handful of data points to uncover one of the city's biggest secrets. He proved that a few clues, if you look at them the right way, can tell you a huge story about the bigger picture. Now, John Grant only had a few clues to work with, but today we are drowning in data. It's everywhere. So the very first job of any modern data detective is just to organize all that evidence, and that's where something called descriptive statistics comes in. It's all about making sense of the chaos before we can even think about drawing conclusions. So, the most basic first step is just to get your data into a clear, organized format. Take a look at this table of average pay by state. It's really just a list of numbers, but by putting the 2 years right next to each other, you can immediately start to see trends and compare states. It's how you go from just a messy pile of numbers to a coherent piece of evidence.
Let's be honest, a picture is worth 1,000 data points, right? When we actually visualize that data, like with this bar chart here showing university funding, the story just pops out at you. You don't have to read every single number. You can see in a split second that Johns Hopkins is way ahead of the pack. Visualizing your clues helps a detective spot the important stuff right away.
Okay, now for what I think is the most exciting and maybe the most dangerous part of the whole investigation, what we call the inferential leap. Once our clues are all neat and organized, we use the evidence we have from our small sample to make a big conclusion about the larger world we haven't seen, the entire population. So what is inferential statistics? It's basically the set of tools that lets us do what John Grant did. It's the science of making a really educated guess about the whole group based on just a small piece of it. It's incredibly powerful, but, and this is a big but, it's also where an investigation can go completely off the rails.
So let's break down the core idea. The population is everybody, the entire group we're curious about, like all voters in a country. Now, obviously, we can't talk to every single one of them, so instead, we study a sample. Just a small part of that group, like 1,000 voters we call on the phone. And the number one goal, the most important thing for any good detective, is to make sure that small sample is a perfect mini version of the whole population.
And what happens if it's not? Well, you get a total disaster, like the 1936 Literary Digest poll. They surveyed millions of people, a massive sample, and they predicted a huge, easy win for Alf Landon. But they were spectacularly wrong. Why? Because their sample was totally biased. See, during the Great Depression, they mostly surveyed people who owned cars and telephones. In other words, wealthier folks. The huge lesson here? A giant sample size means absolutely nothing if it isn't representative. This brings us to what I like to call the detective's deadliest trap. It's not enough to have a good sample. You have to know how the clues were gathered. This is the crucial difference between just noticing that 2 things tend to happen together and being able to prove that one thing actually causes the other. And this This is the absolute showdown. On one side, you have an observational study. Think of yourself as a detective watching from across the street. You just observe, you measure, you take notes. You can find links or associations. But on the other side, you have a designed experiment. Now you're not just watching anymore, you're getting involved. You randomly apply some kind of treatment and see what happens. And that one little word, randomly, that's the golden key. That is what lets you prove cause and effect. Let me show you with 2 real cases.
So, case file number 1. An observational study looked at health records and found that men who'd had vasectomies also had higher rates of prostate cancer. A link was found. But, and listen closely, they could not say that vasectomies cause cancer. Why not? Because there could be a third suspect, some other hidden factor. Maybe it's a lifestyle choice or a genetic trait that's common among those men that's the real culprit. The investigation is still open.
Now let's contrast that with a study on folic acid. Here, the researchers ran a proper designed experiment. They took a group of pregnant women and randomly assigned them to one of 2 groups. One group got folic acid, the other got a placebo, a sugar pill. The results? They were dramatic. The group that took the folic acid had a way lower rate of birth defects. And because the only real difference between the 2 groups was the folic acid, thanks to that random assignment, the researchers could say with confidence, folic acid helps prevent these birth defects. Case closed.
So, we've traveled from 17th century London all the way to modern medicine. We've seen how these ideas work. And now it's time to hand the magnifying glass over to you. Because with these tools, you can absolutely become your own data detective.
So here it is, your official detective's toolkit. The next time you see a shocking headline or a new study, just run down this checklist. First, question the sample. Who did they talk to? Does it really represent everybody? Second, identify the study type. Were they just watching, or was it a designed experiment? Third, and I want you to burn this into your brain, beware the causation trap. Correlation does not equal causation. And finally, look for that magic word, random. Random assignment is the gold standard for proving that one thing causes another.
We live in a world that is just overflowing with data, with clues. It's never been more important to be able to tell a solid investigation from a sloppy one, to spot a real conclusion versus a false lead. The clues are everywhere. The data's out there. Now it's your turn to start asking the right questions.